Okay, now that we have gotten to a point where we wrote the BFS algorithm formally, we described the entire algorithm, let us illustrate how this algorithm would work, how it will make use of the queues, and how it will compute the distances. This is the algorithm, this is the pseudocode of the algorithm, and this is an example of a graph that we have been working with. Remember, this is an algorithm that takes as input a graph, like this one, a source node. In this case, I'm going to assume it is 0. And it's going to compute the distance dj to every node j from node 0. Okay? So in this case, this is our graph, and the initial node I is 0. Okay? So how is this algorithm going to work? We will keep track of dj's. The first thing that the algorithm does is that it initializes q to an empty queue. So we start with, I'm going to have q here. It's going to be an empty queue. Okay? And this is the first thing in the first line. Then it says, for every node j, initialize the distance to infinity. So we are going to have now d0 equals infinity, d1 equals infinity, and d3 equals infinity, d4 equals infinity, d2 equals infinity, and d5 equals infinity. This is, now we are done with lines 1, 2, and 3. Then the fourth thing, it says di is 0. Let's set di to 0. I is the specific node that's part of the input. So we are going to go, since the I is 0, we are going to go to node 0 and now reset its distance to 0, from infinity to 0. Okay? So now this distance is 0 here. Okay? And the next thing we will do is that we will push that node I onto the queue. So now the queue is going to have node I, which is 0. I is 0, therefore the queue is going to have 0. The convention I'm going to use is that the head of the queue is on the left, the tail of the queue is on the right. So every time I add something to the queue, I'm going to add it on the right. Every time I take something out of the queue, I'm going to take it from the left. So now after line 5, we have distance to node 0 is 0. The distance to every other node is infinity. The queue has only one element on it, which is node 0, the initial node. Then we go into this while loop. And this loop says, as long as the queue is not empty, do the following work. We look at the queue. Is it empty? The answer is no. So we go into this loop and start doing work here. What it says first is j is dq of q. So take an element from the queue. Remember, this is not a random element. This is not any operation we can have in mind. This says that remove the element that's at the head of the queue. So in our drawing there, remove the leftmost element in that list that I'm showing. J is going to take that node. So now at this point, J is the element at the queue. J is going to be 0. Okay? So it's going to, when we do dq, then that element, not only do we see what's in the head of the queue, but we also remove it. So dq removes the element from the queue and returns it to us. So now after this step, I have the queue is empty. Okay? So now j is 0, the queue is empty. Then we say for each neighbor h of j. For each neighbor h of j, what are the possible values of h? J is 0. I go now to the graph. I say, okay, what are the neighbors of this? For each neighbor, it's going to go through them in some sort of order. Okay? There is no specific order. It doesn't have to go 1, 3, 4. It can go 3, 1, 4, or 3, 4, 1, or 4, 1, 3, and so on. We can use, for example, let's just, to make sure that nobody misunderstands things, let's assume that it's actually going to try the neighbors in the order of 3, then 1, then 4. Okay? So first it's going to go to h. The first neighbor is going to consider is going to be node 3. Okay? So it says for each neighbor, the first one is node 3. If dh equal infinity, do. Is d of 3 infinity? The answer is yes. So this condition holds. So we come to this point here. That when we come here, we say dh is dj plus 1. Sorry. This is dj plus 1. dh is dj plus 1. dj, remember j is 0. It's d0 plus 1. d0 is 0. d0 plus 1 is going to be 1. So now d3 gets updated, and its distance is 1. Okay? Once we update the distance to node 3, we push that node into the queue. So now the queue, which was empty, we put the node h. H is 3, so 3 goes into the queue. Okay? We are done with node 3. We come back to this loop for the next neighbor of node j, which is node 0. We said that the next one we are going to consider, for example, is node 1. So we come to node 1. Now we look at h equal 1. We ask, is d of 1 infinity? The answer is yes. What we do is we update the distance of 1 to be d of 0 plus 1, which becomes 1 now. And we push this node 1 onto the queue. Remember, it goes onto the tail, so now the queue is going to have node 1 also. Okay? We are done with node 1. We come back now to other neighbors of node 0. The next neighbor is going to be 4. So now h is 4. Okay? H is 4. We ask, is d of 4 infinity? The answer is yes. We come here, we update d of 4 to be dj plus 1, d0 plus 1, which is 0 plus 1, which is 1. So this is updated now. Once this update, we add the node 4 onto the queue. Again, it is added to the tail. Okay. Now we come back to this loop, say for each neighbor, are there any more neighbors of node 0? The answer is no, so we are done with this. Okay, we are done with this for node 0. We exit from here, we come back to this loop that says while queue is not empty, do. Is the queue empty? The answer is no, so we come back to this inside this loop. Since the queue is not empty, the first thing we do is that j is the element at the head of the queue. Now, when we look at the queue, what is the element that's at the head of the queue? It is 3. So j now is node 3. Since we dequeued it, it is gone from the queue. And this is what the queue now, the state of the queue is. We have node 3 here. We now ask for every neighbor h of j. J is 3. Now let's look at every neighbor of node 3. So what are the neighbors of node 3? It has 2 neighbors, 0 and 1. So the first one is h is 0. We ask, is d of 0 infinity? The answer is no. So this doesn't work. We don't come inside this. The condition doesn't hold. We come to the other neighbor. H is 1. The other neighbor of node 3 is 1. Is d of 1 infinity? The answer is no. We don't come here. Then we ask, what about other neighbors? There are no more neighbors. We are done. Okay? So actually, when we came to node 3 and we looked at all of its neighbors, since none of them had a distance infinity, actually there was nothing done by the algorithm here. Okay? So now we come back and say now, is the queue empty? The answer is no. We say remove an element from the queue and put it in j. This now becomes j now is 1, and the queue is in this state. Now we go to node 1. We say for every neighbor h of node 1, do. What are the neighbors of node 1? There are 0, 3, and 2. Okay? So the first h is going to be 0. We are going to come here, is d 0 infinity? The answer is no, we don't do anything. We look at another neighbor. Another neighbor of node 1 is node 3. Is d of 3 infinity? The answer is no, we don't do anything. We come back to our next neighbor. The next neighbor is 2, node 2. Is d of 2 infinity? The answer is yes. So now we say d of h is 2, d of 2 is d of j plus 1. J is 1, so this d of 2 is going to be d of 1 plus 1. D of 1 is 1, plus 1 is going to be 2. So now this gets updated. We put this node h on the queue. So node 2 now goes onto the queue, and it goes again on the right. Okay. Now we are done with node 1. There are no more neighbors of it. We come back to the queue. We come back to the queue. We said, okay, now remove an element from the queue and put it in j. The next one is going to be 4. So j now is 4. And now what happens here? For 4, we say, okay, let's look at all the neighbors of 4. The first neighbor is going to be 0. H is 0. We say, is d of 0 infinity? The answer is no, so nothing happens. We look at the next neighbor of 4. Next neighbor is 2. Is d of 2 infinity? The answer is no. We don't do anything. We look another neighbor of 4, which is 5. So now h is 5. Is d of 5 infinity? The answer is yes. Since d of 5 is infinity, we update its distance. D of 5 is going to take d of 4 plus 1, because j is 4. D of 4 is 1 plus 1 is going to be 2. We update this to 2. And we put h onto the queue, which is node 5. Now node 5 goes into the queue. And again, because I forgot, since j is 4, we had to dequeue it first. So it's not there. And this is now the state of the queue. We come back to this line. Is queue empty? The answer is no. We dequeue the queue. We get an element from it. It's going to be 2. Once we get 2, j is 2 now. J is 2. We look at all the neighbors of j. It has 2 neighbors h. It has neighbor 1 and neighbor 4. But d for both of these nodes is not infinity, so we don't do anything. So once we look at 2, its neighbors, the distances have been computed. We don't do anything. We remove 2. We are done with 2. We come to the queue. Is it empty? The answer is no. We take the element on the queue. J, in this case, is going to be 5. And the queue is going to be empty now. We come to 5. We ask about all the neighbors of 5. It has one neighbor, 4. Is d of 4 infinity? The answer is no. D of 4 is 1. We don't do anything. We come back to the queue, to this line. While queue is not empty, we look at the queue. It is already empty. So we don't do anything here. We come to this line. We say return d. D0 is 0, D1 is 1, D3 is 1, D4 is 1, D2 is 1, D5 is 2. So we are done. This is how the algorithm would run. Now notice that if there was, again, node 6 here that is not connected to anything, this node would not have been added to the queue at any point. In the initialization step, it would have gotten D6 equal infinity. And by the time we have finished the algorithm, it wouldn't have been touched. Therefore, when we return D, it would have returned D6 infinity. Okay? And this is how this algorithm works.